All right, so what we're gonna do is we're just gonna take a look into what the grade 12 course looks like. And I don't know if it's gonna be harder than this, but we will prepare you for any possible question they could ask you at this level. Are you in the AP class? Does your school have like AP or gifted or
Yeah, I'm in AP.
you're in AP Maths?
Mm-hmm.
Okay, cool. So that means you'll probably learn calculus as well. So keep that in mind. In AP, they usually kind of put in university first year courses, okay? One
Mm-hmm.
of which is like calculus. So let's look into this. Shouldn't be too difficult. All right, let's look at this one. Use reasoning to decide whether a relation is a function. Now, you know what a function is, right?
Mm-hmm.
It's something in this form, but there's some restrictions. I'll tell you what it is. The main restriction for something to be a function is that it has to pass the vertical line test, like this. It can only cross one point on the curve. If it crosses 2 points, so let's say you have a curve like this, and when you draw a line, let's say it crosses multiple points, then that is not a function. This one, on the other hand, it's not crossing more than one point at any given point on the curve, so that is a function. Very simple, you just draw a straight line. What about B? Is B a function? It's hard to tell, yeah? It's hard to tell. It is, right? It is. So let's prove it. So the goal is, what does 1 over x squared even look like? What kind of a function is this? How would you define this? Is it a quadratic? Is it cubic? Is it a sine function? What's the name for this? Notice it's in the denominator. What you're interested in is in the denominator, and there's a 1 on top.
It's a reciprocal
It's a
function.
reciprocal function, right? So now the goal is we want to see whether this is a function or not. Let's graph it. So how do you graph a reciprocal function? Always start with the baseline, by the parent function, I mean, when I say baseline. So y equals x squared is your baseline, the parent function. What we're going to do is we're just going to make a rough sketch of y equals x squared. Looks like this. And that's just y squared x squared. Y equals x squared. Now we want to graph 1 over x squared. Now the difference between x squared, both of these are y's. Y equals x squared, y equals 1 over x squared. The only difference between these two is that in the reciprocal function, all the y values are flipped upside down. They're all 1 over the original y value. Yeah?
Mm-hmm.
Whatever the y value was for the original function, for the reciprocal function, you just flip it upside down or do 1 over. So we don't really have points here, but we don't really need points. This is a very large number, right? It's a very large positive number. When you do 1 over a very large positive number, what do you get? A very small, right? Positive
Mm-hmm.
number, right? The sign is important. When you do 1 over a very large positive number, you're going to get a very small positive number. So both of these points up here, I'm just arbitrarily calling them a million. They're going to come all the way down next to the x-axis. They're going to become very, very small. So these points come over here. What about this point? What's the y value here at the vertex for the parent function?
It's 0.
A 0. So when you do 1 over 0, you're going to get an asymptote. You can't have a 0 in the denominator. Anytime there's a 0 in the denominator, there's going to be a vertical asymptote, and that's what this is. Now we just need a few more points. Let's think about this point right here, this point. So right now, it's a very small positive number. So let's say it's 1 over 0.00001. It's a very small positive number, this point right here. So when you do 1 over a very small positive number, what do you get? You get a very
A bigger
large
number.
positive number. Yeah, exactly. You get a very large positive number. So this point on the original function is going to shift all the way over here. It's going to become a million. Same thing here, because this is symmetrical. This point here is also going to go all the way up. And then in y equals x squared in the parent function, it's going to go through a y value of 1. So let's say this is a y value of 1. This point and this point. The y value there right now is a 1. What's going to be the y value for the reciprocal function? Is it going to change? No. Okay. Right now, the y value is 1 for the parent function. And so when you go to do 1 over x squared or 1 over 1, you still get a 1. So those points don't change, okay? So these I'm going to call them. I don't know what the book calls them. I don't think the book really labels them. I'm going to call these something. These are called stagnation points. Or maybe stationary points. They don't change for the reciprocal function. So we know we go through here. We know we go through here. Now all we have to do, reciprocal function, we already have a vertical asymptote. Is there any other kind of asymptote for a reciprocal function? A reciprocal function always has a horizontal asymptote on the y-axis. Okay? Every single time. If you see 1 over a function, right, 1 over anything, it will always have a horizontal asymptote on the x-axis. So here's another asymptote. So now all we have to do is connect the points. We have 3 points. We have the stationary point, we have a very small positive, we have a very large positive, and then you just kind of ride the asymptotes. Remember, you cannot cross the asymptote. So it goes all the way up there. There's no way it crosses this asymptote, so it's going to ride it forever to infinity. Same thing for this other. So now ride this to the x-axis. It'll never actually reach the y value of 0, but it's just going to ride it to infinity. So therefore, the graph of 1 over x squared looks like this. Is that a function?
Yes.
Yes, it is. What's the domain of this function? So domain means the possible x values it can take. If you look at the graph, there's only one x value that it cannot take.
0.
0. So the domain is going to be XER. I'm going to show you both notations. XER, X cannot be 0. That's in your set notation. In interval notation, it'll be negative infinity to 0, union 0 to positive infinity. So everything except 0. And 0 is exclusive. That's why these are not square brackets. Okay? And infinities are always rounded brackets in an interval notation. Can't be 0. That's why these are rounded. Cool? So that's the domain. What about the range?
It has to be greater than 0.
It has to be greater than 0. Perfect. Y is greater than, not equals to, strictly greater than 0. So in the other notation, it'll look like 0 to positive infinity and rounded brackets because 0 and infinity are, neither of them are included. And you're done. So again, just a reciprocal function, not too difficult. Always start off with a parent function. And you can just use this trick, the one that I use. What does 1 over a very small number become? What does 1 over a very large number become? What you need to take into account is the sign, though. Sometimes it's a little bit tricky here. Let's just quickly do another flippity flip. What is this parent function? It's a polynomial. So what is it? Is it x squared? No, it's x cubed. X cubed. So now let's say the question is like graph 1 over x cubed. So graph the reciprocal function 1 over x cubed. All right, let's begin. Step number 1, asymptotes. There is always going to be a horizontal asymptote for reciprocal functions. No question asked. What about a vertical asymptote? Is there a vertical asymptote for this? So for this function, right, for this function, is there any value of x that would give you a 0 in the denominator? That's what vertical asymptote is. What value of x gives you a 0 in the denominator? What is it? It's a 0.
0.
Yeah, exactly. It's a 0. So there's also going to be a vertical asymptote. So we've dealt with the asymptotes. Now what? Now notice you'll always have a stationary point. Over here, it's the y value of 1, right? Over here, it's the y value of -1. Both 1 and -1, when you flip them upside down, do they change? No, they don't.
No.
So these are going to be your stationary points. They're always going to be at once. It didn't apply to the last question at -1 because we didn't go underneath the x-axis, but here it's going to be -1. That's going to be a stationary point. So this y value here is a stationary point. This y value here is a stationary point. Okay? Both of these are a +1 up there and then -1 down there. Now we just need a few more points. Let's think about this. It's a very large positive number right now. This point right now is a very large positive number. When you flip it upside down, what do you get? You have a very large positive number. When you
You
flip it
get a
upside,
really small number.
a very small number, exactly, over here. This right now is a very large negative number. The sign is important. It's a very large negative number. So when you flip it upside down, what do you get? You get a very small positive number or negative number?
Negative.
Negative. So this point is going to come all the way down here. Now we just need one more point. Let's think about this point and this point. So both of them right now, well, depending on which one you're looking at, let's look at this one. It's a very small positive number, right? It's a very small positive number. So when you do 1 over a very small positive number, what do you get?
A really big number.
A very large positive or negative?
Positive.
Positive. So that point there, the one highlighted in yellow, is going to come all the way over here. And then you just connect the dots and make sure you write the asymptotes. Boom, that way, this way, and then when you do the math down there, you'll see that it's going to be symmetrical. So you'll get something like this. So is 1 over x squared a function? Sorry, 1 over x cubed. Is 1 over x cubed a function?
Yes.
Yes. Okay, so that's how you graph reciprocal functions. It's not terribly difficult. You just think about a very large positive, very large negative, and stationary points. Let's look at C. They've given us, what is this called? Bubbles. I don't think that's the technical name for this. It's most definitely not a bubble. Okay, it doesn't matter. When they give you something in this form, okay, when you have two bubbles, the one on the left is the domain, the one on the right is the range. So from this, it's a little bit difficult to see whether or not it's a function. Because remember, for something to be a function, it has to pass the vertical line test, yeah?
Mm-hmm.
So it's not super obvious if this is a function or not. So what we can do is we can straight up plot those points. So the first point is -2, 0. So right there. The next point is -1, 1 here. Next point is 0, 1 here. 1, 2 here. 2, 3 here. So it looks like our curve, when you connect the dots, looks something like that. Is that a function?
Yes.
Yes, it is, right? And easy as that. So the domain are these numbers, the range are these numbers. So let me show you an example when it won't be a function if they give it to you in this form. And here's the trick. If you see, look at the arrows, okay? It's always going to be domain on the left, range on the right. I'm looking at the arrows. The 1-to-1 arrows, like these are called 1-to-1. You can completely ignore them. They are not going to dictate whether or not something is a function. It's the 1-to-2 arrows that dictates this. And here's the rule. If you have one x value, okay, one x value going to 2 or more y values. It is not a function. So what does that look like using arrows? Using an arrow, let's say you have, I'm going to use 0, right? 0 is here. That's one x value, and then this goes to 2 different y values. Something like this. Then it's not going to be a function. Why not? Well, let's graph it. So you have 0, 1, this point, and then you have 0, 2, this point. Does that pass the vertical line test?
No.
No, it does not. So that's the trick. When they give you these bubble thingies, if you see a less than sign, this is a less than sign in the arrows, then it's automatically not a function. Greater than sign is fine. By greater than sign, I mean this one right here. The 1 to 1s, you can ignore them. You're strictly looking at 1 to 2s. And if you have 1x going to 2 or more y's, then that's not a function because it does not pass the vertical line test. Okay, so this is the technical name for this, right? Mapping diagram is what this book calls it. Mapping diagram. This next question is very difficult. Maybe we'll ignore it for now because this one is talking about trig and then we have to graph it out. It's a little bit annoying. Okay, so automatically remember the sign that you're looking for is this, okay? In these mapping diagrams, you're looking for this. If you see this, it's not a function. Is A a function?
Yes.
What about B?
Yes.
What about C?
No.
Okay, yes, I mislabeled them, but yeah, this is not, this is good, this is good. So easy as that, right?
Mm-hmm.
But B, D, and F are a little bit more trickier, but the same principle applies. If you have one x value going to 2 different y values, it's not a function. 1x to 2y, it's not a function. So this is the rule. You don't have to really graph these. You could, but you don't have to. So let's look at B. Do any of the x values repeat? No, it does not. All of them, x doesn't repeat. So you're good. What about D? Is D a function?
No.
No, it's not because you have 2, 5, 2, 7. You have 2 going to 5 and 2 going to 7. That is not a function. It's out. What about F?
It is.
It is. These two are very simple. A is obviously a function. B is obviously not a function. Let's look at these other guys. So what does it say? It says determine whether or not it's a function and then find its domain and range. All right, cool. Let's look at C. Is C a function?
Yes.
Okay, how do you know? What kind of a function is it?
It's a polynomial.
Well, yeah, it's a polynomial. Is it quadratic, cubic?
Quadratic.
Quadratic polynomial. Yes, it's for sure a function. But the question's asking us for the domain and range, and that's where things get a little bit tricky. So what I'm going to do is I'm going to rearrange this. So tell me if you disagree. Y will be x squared. Do you agree or disagree? Looks good to me. So that's your function, right? X squared over 2 minus y over 2. The question's asking you for the domain and range. It's a polynomial function. What's the domain of a polynomial function?
XER.
XER. Now this function, the range is going to be tricky. How do you find the range of a quadratic? You're looking for the vertex, okay? In a range for a quadratic, you're always looking for the vertex. It's either going to be y is less than something or y is greater than something. In this case, it'll be y is greater than something because it's opening up. So now we have to find the vertex of a quadratic. How do you find the vertex of a quadratic function? There's many ways. I'll give you the one that I like. I think is the best. You can always complete the square. This is the best approach. The vertex is always going to be in this form, h comma k. When your equation is in the standard form, when it's in this form, h, the x value of the vertex, is minus b divided by 2a. So let's use this approach. Up here, what's my a value, what's my b value, and what's my c value? You're comparing this equation to this equation. A is the number attached to x squared. What's a?
It's 1/2.
It's 1/2. I'm just going to write that as 0.5. What about b? B is the number attached to the x power 1 term.
There isn't one.
There isn't one. So what do you put b as?
0.
0. C is also negative 0.5, right? So when you go to find h, you'll see that you're doing 0 over something. You get an x value of 0. So your vertex is at an x value of 0. When the x value is 0, what's the y value? Negative 1/2. Yeah? Negative 1/2. So we found the vertex. The vertex is at 0 and negative 1/2. So what's the range? Remember, it's opening upwards. So it looks kind of like this. And this point right here is 0, negative 1/2.
It needs to be greater than negative 1/2.
Can it be exactly equal to negative 1/2?
Yes.
Yes, because it's a quadratic. So negative 1/2. There we go. Not super difficult. So yeah, you're going to have to find the vertex, and there's many ways to find the vertex of a quadratic. Let's look at d. Is d a function? X equals y squared. Is that a function? It's not obvious from this. You always have to write it in terms of y. If x is y squared, I just want y on one side of the equation. What do I do on both sides?
You square root.
You square root. What's the square root of x? Is there a plus minus or no?
There is.
There is. At this level, there's always going to be a plus minus whenever you square root a letter, a variable such as x. So now what? Okay, cool. So we have a square root function. Remember, y equals root x looks like this. Yeah? Y equals negative root x was just a reflection on the x-axis, so it'll look like this. So on the bottom, we have negative root x, and on the top, we have positive root x. And y is a combination of both of these functions. Is this a function?
Yes.
No, it's not. You're looking at it as a whole. You're looking at this as a whole. Because y is a combination of this and this, okay? So you're looking at the bigger picture here. Again, is that a function?
No.
No, because it doesn't pass the vertical line test, right? So it is not a function. Well, we could state the domain and range of this relation. So if it's not a function, we call it a relation. And we could state the domain and range of this. What happened to my curve? Okay. So this is the origin. I got super confused. This is the origin right here. What is the domain and range of y? Can it be negative? Look at the x values. Can it ever take a negative value?
No.
No, it cannot be. So domain is going to be x is strictly greater than equal to 0. Equal to 0 because x squared, the inverse function, can take values of 0. That means root x, the inverse function of x squared, can also take x values of 0. So that's why it's inclusive. What about the range?
It can be anything.
Can be anything, YER, and you're done. Cool? Not too difficult. E, we've done it a few times just today. What kind of a function is E? It's a reciprocal function, okay? E is a reciprocal function because x is in the denominator and there's nothing on the top. If there was x both on the numerator and the denominator, then that would be a irrational function. So what's the question asking us? Graph it, domain and range. All right, I'm just going to rush this. We've already kind of done this. The 3 on the numerator, all it does is it stretches the y value by a factor of 3. It does not change the asymptote. In a reciprocal function, there's always going to be a horizontal asymptote. And here, where's my vertical asymptote? What value of x gives me a 0 in the denominator?
0.
0. So you have a vertical asymptote at x equals 0. So these are the asymptotes. This 3 doesn't affect it much. Your curve will look something like this. That builds from the fact that 1 over x looks like this. The only difference between these two is that the y values here are going to be 3 times as much. Okay? They're going to be stretched 3 times as much. And we'll graph this to show you. So I don't have any points. So here's a sketch. Just make sure you understand this. What do I mean by that the y values are 3 times as big? So for any x value that you pick, let's say we pick an x value of 5. The red curve is 1 over x. The y value there is 0.2. Okay? At 5, it's about 0.2 on the red curve. But 3 over x, the y value there is 0.6. So every y value is just stretched by a factor of 3. It doesn't change any of the properties of the curve. It doesn't change the domain. It doesn't change the range. The only thing that changes the domain and the range are translations. Translation means shift, left, right, up, down. That's the only thing that changes domain and range. A horizontal or a vertical stretch, like in this case, it's a vertical stretch, that doesn't change the domain and the range. So the domain and the range of this 3 over x is going to be the exact same thing as the domain and range for 1 over x. What's the domain? What are the possible x values this function can take?
Anything but 0.
Anything but 0. What about the y values?
Also anything but 0.
Right. And you're done, okay?
Mm-hmm.
Part F is super simple. That's just a linear line. Not gonna spend too much time on it. It looks like this, XER, YER. Done. Linear is very simple. I don't reckon we'll be doing a lot of linear. anything else. This looks wacky. Determine an equation for g of x. Okay, cool. Just looking at the table of values, okay? Look at the table of values. Is it linear or no? So you're looking for the slope, right? All the x values, they're all going up by 1 every single time. So are the y values going up by the same amount every single time?
No.
No, they're not. So this is not a linear, okay? So what is this? I guess let's find out. 0, 3. And we're also going to be doing some modeling on this. We'll use some Excel, see what it spits out. 1, 4. This is not going to be to scale, so I don't know if we're even going to figure out what this is. 2, 7. 3. Yeah, this is not going to work. It looks like a quadratic. Could potentially be an exponential. Let's graph this. To scale is what I mean. And I've shown you how to do this before, yeah?
Mm-hmm.
So you have your x, you have your g of x. Let me tell you, the title isn't that important. This is just for you. The labels are not important. What's important are the numbers that you feed into it. So 0, 1, 2, 3, 4, 5. Then we have 3, 4, 7, 12, 19, 28. So you have your x and your y. And now all you do, okay, all you do is you highlight your table. This is my table. Go to insert, go to charts, and we're interested in a scatter plot. Scatter plot is the one that has a bunch of dots on it. So this one, and click on the first thing you see, okay, right there. The first thing you see. And you'll get this curve. It looks okay, right? It looks okay. It looks pretty decent. What you can do is you can even make it fancier. So let me just show you what I did here. In a plot, right? In a plot, you'll never have a title on the plot itself. What do I mean by this? Now I'm gonna have to show you what I mean by this. And it's always more difficult than it sounds. Let me see if I can find a paper here. All right, yeah, I found something. So here's a random paper. We're not interested in anything here. But notice in the plot itself, there's no title, right? What we do with plots is that the caption, we call it, you have to caption a plot underneath it. You never type a title within it. You'll never see a plot with a title. So that's what I was trying to do here. I was trying to kill this g of x title. So let's kill this. And if you notice in those plots, they didn't have the vertical lines like these guys or the horizontal grid lines. They didn't have any of these. So we're going to delete the vertical ones. We're going to delete the horizontal ones as well. And then what we could do is we could add axis titles. So on the x-axis, we know this is the x value. On the y-axis, we have g of x. So there you go. That's what your plot should look like. And then in the final step, because the question was figure out an equation for this, we're going to click on the dots. You have to click on the points, right click, add a trend line. Trend line is a curve of best fit. So it'll try to fit a curve, any function that you really want, and it'll fit through it. The default is going to be linear, but we're going to see that linear is not a best fit. So what actually tells you how good of a fit is your curve? What gives it away is the r squared value, okay? R squared. R squared of 1 means it's a perfect fit, which is very, very unlikely in real life. But this is a made-up question with 5 points, so maybe we'll get R squared value of 1. But the point so far is that this function is not linear, which we knew, right? Which we know because the slope wasn't constant. So let's try something else. What do you think this is? You have options on the right side. Exponential, logarithmic, polynomial. What do you think this function is?
Exponential.
Exponential? All right, let's try it. Ooh, exponential is good, but it's still not 1. Maybe that's the best we could possibly do. Let's try polynomial. There you go. What's a better fit? Question for you. This is exponential. Look at the r squared value. This is polynomial. Look at the r squared value. Which one is a better fit?
Polynomial.
Polynomial. So this is a polynomial function, okay?
Mm-hmm.
But the question asked us for the equation. What is the equation? Well, it's very simple. Scroll down here a little bit, and you'll see that there's an option called display equation on chart. So that's going to be our equation. I'll show you exactly what all of that means. The r squared is how strong your model is. R squared equals 1 means it's a perfect fit. This is as good as it gets, cannot get any better. So that's good. The only weird looking thing here is this. What does that mean? 3e to the negative 14. So this is a scientific notation thing that they've done here, that Excel does, that actually a lot of computer softwares automatically does. Why? Because what it means is this. E means 10 to the power of, okay? E means 10 to the power of something. So here, 3e to the negative 14 means 3 times 10 to the negative 14. Is that a big number or a small number? The question is that a large number or is that a small number?
A small number.
A very, very, very small number, right? What this means is that 10 to the power of 14 means you have 0 point, okay? You have 0 point, and then you have 14 zeros, okay? Like this, 14 zeros, and then you have this 3 at the end. So it's a very, very small number, okay?
Mm-hmm.
It's basically negligible, and that's what we're going to do here as well. We're completely going to ignore that 3e to the negative 14. That's just something Excel fed us. So our actual equation is going to be y equals x squared plus 3. And you'll see that for every point, it works out nicely. Cool?
Mm-hmm.
How could we have deduced whether or not this was... Yeah, so this is a good question. So you said exponential. It looked exponential, right? But we're using technology. How can we deduce what kind of a function this is by hand? So it has to do, okay, it has to do with the first difference, okay? Remember this. Your x values are redundant. So you have your y values. You have 3, 4, 7, 12, 19, 28, 19, 28. So these are your y values. And then what we're going to do is we're going to find the first difference. Doesn't matter from up to down or down to up. I like positive numbers, so I'm going to subtract down to up. 28 minus 19 is a 9. 9 minus 12, 19 minus 12 is a 7. 12 minus 7 is a 5. 7 minus 4 is a 3. 4 minus 3 is a 1. So if your first differences are equal, if they were all 1, 1, 1, 1, 1, or 5, 5, 5, 5, 5, it would be linear, okay? If the first differences were the same. If the first difference was a multiple of a number. So what do I mean by this? Let's say you have 2, 4, 8. Notice how it's being multiplied by 2 every single time. So times 2, times 2, times 2, times 2. This is what I mean by here. You're multiplying by the same number to get to the next digit. If your first difference is a multiple of a number, then it's exponential. So is this either linear or exponential?
No.
No, it's not. So what do you do from here? You go to the next difference, second difference. So again, I'm going to go down to up. So 2, 2, 2, 2. So the second differences are equal. What does that mean? What kind of a function do we have? It's a quadratic, okay?
Mm-hmm.
Second difference is equal. It's x power 2. Means it's x power 2. Third difference is equal. What do you think that is?
Cubic.
Cubic, exactly. So we could have deduced what kind of a function it was. We know it's a quadratic, and then you just kind of like trial and error to see what the y-intercept is. So in this case, the y-intercept, we already know it was +3, but you could have trial and error this. So that's the answer to part A. Part B. Does G3 minus G2 equals G3 minus 2? All right. On the left side, we have G3 minus G2. What's G3?
It's 12.
Well, what's G2?
7.
That answer is a 5. So on the left side, you get a 5. What's G3 minus 2?
It's 10.
It's 10? How'd you get 10? It's not 10. So G3 minus 2, you have to do the brackets first, right? So you'll just do 3 minus 2 inside the bracket. You'll get G of 1, okay? And that gives you 4. So on the left side, we have a 5. On the right side, we have a 4. So they're not equal. Cool? That's it.
Mm-hmm.
So this, you want to do it's BEDMAS, right? So you have to do the brackets first. How'd you get a 10? What'd you do? Vaguely curious what you did to get a 10. Okay, it doesn't matter.
Okay.
That just comes out to be G of 1. I'm gonna leave that there just in case we need it later. Okay, really, really quickly. Is A a function? What are we looking at here? What is this? It's a circle. Okay? Remember, x squared plus y squared equals 25 is well, it's a circle with, what's the radius? So here, let's just quickly recap the circle stuff. X squared plus y squared equals r squared. This is the equation for a circle with the origin at 0, 0. So r here is 5. It has a radius of 5. And then you could get a more complicated circle, which is this x minus h squared plus y minus k squared equals r squared. This is also an equation for a circle, but now the center is not at the origin. The center is at h comma k. That's pretty much all it for circles. And for any reason, if you see a number, okay, the numbers, the constants, the coefficient of x squared and y squared for a circle has to be 1. So for any reason you see 3 here, a 4 here, something like that, that is not a circle. What is it? It's a little bit difficult to answer. It's an eclipse, okay? It's an eclipse.
Mm-hmm.
So this shape actually, this grade 12 book, this course in Ontario doesn't cover eclipses. So this course has nothing on eclipse. I don't think it's part of the curriculum here, but I have seen that it is a part of the curriculum in BC and Alberta. So you may see this in class. Okay?
Mm-hmm.
It's not terribly difficult. You'll see it is for sure more difficult than a circle, for sure. But there's some rules to it, and once you figure out the rules, it's not too bad. So we know that the left equation is a circle. Is circle a function?
No.
No, it's not. Um, Now the graphing the other thing is not gonna be easy. Okay, let's look at this other thing. How do we even graph this? All right, we'll figure out a way to graph this. So we have, I'm gonna rewrite it. 25 minus x squared. Can you have a negative inside of the square root?
No.
No, you cannot. So that means your 25 minus x squared inside the square root, okay, inside the square root has to be strictly greater than or equal to 0. Do you agree?
Mm-hmm.
So what does 25 minus x squared look like? The y-intercept is 25. Minus x squared means it's going to open upside down. This. It has to be strictly greater than 0. For which y values is this function strictly greater than 0? Sorry, for which x values? So for which x values is the function strictly greater than 0?
Between -5 and 5.
Exactly, between -5 and 5. Can it be exactly -5 and exactly +5?
Yes.
Yes. So we know the domain for this is from -5 to +5, right? -5 to +5 inclusive. So we know, and we're square rooting them as well. So let's make a table of values here. At -5, so this is your x value, 25 minus x squared, and then you square root 25 minus x squared. So I'm going to do it kind of like this. So the y value there is 0. When you square root the y value, you also get a 0. Same thing on the +5. The y value is 0. When you square root, you also get a 0. So we have our boundary values. -5, 0, +5, 0. Now we just need a few more points. I'm lazy. I'm just going to plug 0 in there. If I plug 0 as x, what do I get? It's not as difficult as you think it is. So this is our first equation. I'm plugging x as 0. So what do I get?
25.
25. And if I square root it, what do I get?
5.
5. So when the x value is 0, the y value is +5. Okay, like that.
Mm-hmm.
And you can put in a few more points and you'll see that the curve will look something like this. Is that a function?
Yes.
Yes, it is. Cool, that's it. So that's a square root function. So that's how you'd graph something that looks difficult, but really I just use 3 points. You don't even need a calculator for this. It's just 5 squared and square root of 25. Not too difficult. The next section here goes into absolute value. Again, I don't think it's terribly difficult. What is difficult though is these. So it says express using the absolute value notation. And when it says that, I think okay, no, they want it in this form. They want there to be an absolute value and then some inequality or a sign and then some number. So again, you have your x here, you have some sign, it's usually inequality, and then you have a number here. So they want it in this form. Right now we have 2 equations. They want 1 equation. Okay, so how do we deal with a question like this? It is a little bit tricky. So what I'm going to do is I'm going to graph this out on a number line. When in doubt, graph it out. Remember that rule. Boom, boom. Boom, boom. So those are the possible x values, right?
Mm-hmm.
So now think about it. Your variable of interest is x. The number that you're interested in is 3. Look at what the x values you can take. Are they strictly greater than 3, the absolute value of that x value? Are they more than 3 or are they less than 3? We're thinking about it in terms of the absolute value. So over here, you have -4, right? When you take the absolute value of -4, you get a +4, which is greater than 3. Over here, you have an x value of -5, same idea. You'll get +5, which is bigger than 3. Over here, absolute value of 4 is just a 4, which is also bigger than 3. 5 is just 5, which is bigger than 3. So what's the sign in the middle? Greater than or less than?
Greater.
Greater than. And there you go. That's the answer. So the goal is to use 2 different equations and combine them into one. Okay?
Mm-hmm.
It is a little bit tricky. I am not going to lie to you. Okay, so we have this one. And again, I'm just going to graph it out. This time it's inclusive, so it's going to be closed circles. So these are the possible x values that it can take. I'll give you a hint, okay? Again, it's going to be something like this. There's going to be sign there. There's going to be an 8 there. +8 or negative? Oh, sorry. What's the sign in the middle? So again, think about it, right? Let's pluck a random value. Let's pluck a random value. Let's say we pluck -1. So we can pluck this because it's in our domain. So -1, when you take the absolute value, you get a 1, which is greater than 8 or less than 8?
Less.
Less than, right? Let's pick another value here. Let's pick 6. Absolute value of 6 is +6, which is also less than 8. So what's the sign in the middle? Less than, okay? Less than equal to.
Mm-hmm.
Because any value you pick in this range is always going to be less than 8. Okay, see if you can deduce this one. So you have this, and then you have this. So tell me, absolute value of x, 1, greater than or less than? Then just
Greater.
pluck. Yeah, exactly. Easy, right? Greater. And you're done. Cool?
Mm-hmm.
Once you see it, it's very simple. What if we flip the script? Okay, what about this one? So now they've given us a sketch and we're asked to write it in absolute value notation. Again, it's easier than you think, okay? I promise. It's always going to be x on the left side with an absolute value sign. And then there's going to be a number of interest. What's the number here?
3.
3. So what's the sign in the middle? Less than or greater than?
Less.
Less than. And it's also going to be equals to, because I think those are close circles. And there you go. It's as easy as that. All right, let's call it there for today.
Okay. Thank you.
See ya.